I'd like to take a step back and think about how one can use homology in practice in data analysis. So in practice, when you are given a data set, most of the time, it's a point cloud. It's a finite subset of the Euclidean space of some dimension, each dimension representing the coordinates, the data, the observation you obtained. And of course, the data sets are finite. So they are finite point clouds. And finite point clouds does not have any interesting topology, right? The beta 0 of a point cloud is its number of connecting components, and beta 1, beta 2, etc. are all 0. When we do topological data analysis, we think of our point cloud as a sample of an object, another topological space, another subspace, which has some interesting topology. For instance, here, X can be seen as a sample of the circle, right? So M here, the circle, would represent the underlying topology of the data. And we want to understand this topology. Okay, this is the whole idea of topological data analysis. So how can I understand the topology of M when I am just given X? Okay, so we'll start with this part, thickenings. I here rephrase the problem theoretically. Say that there exists a bounded subset, M, a subset of the Euclidean space, that we do not observe directly, but that we observe via a finite sample. And the question is, please estimate for me the homology groups of M from the simple observation of X. And as I said, X, as it is given, does not give us the homology of M. We can do something, and this is called thickening. For every t, a real number, non-negative, I define the t thickening of X as the set of the points of the ambient space that are a distance at most t from X. And I denote this set xt. For instance, X 005 with t equals to 005 is this subset. I thicken my subset X. X01 looks like that. Okay, this is the set of points of the Euclidean space that are 0, 1 close to X. This is X02, X03, etc. X04. This is a 05 thickening, and it never stops. We can consider X09. And notice that something happens. At some point, when I thicken my set, I obtain a circle here. For X equals to t equals to 0,3, I have a subset of the Euclidean space that is homotopy equivalent to the circle, right? You have a retraction of this kind of annulus on the inner circle. Here, this is still true. And there is some point here where all these balls meet, and we do not have a circle anymore. This is something which has the homotopy type of a point. So what I said is that at some point, my thickening will have the homotopy type of a circle, right? And this is true for many values of t. And if I can grab these thickenings that have the homotopy type of the circle, then I will be able to compute the homology of the circle, right? So for instance, here I picked x03. All the Betti numbers of x03 are the same as the Betti numbers of M. And this is very nice because remember that we do not observe M. What we only know are the points of X. Okay? So if I'm able to estimate these thickenings, I will be able to compute the homology of M.
Rafael, can I ask you something?
Yeah, please.
Maybe it's just my intuition, so maybe it's wrong. But let's suppose, for example, that M is compact.
Yeah.
And then do we have any result like if M is compact, then for a sufficiently small t, the thickening is going to be a different, M is going to be like a deformation retract of the thickening or something like that.
We have a result like that, and it's very important for the theory to work. And I will we will prove something like that in 10 minutes.
Okay.
But yeah, exactly.
Okay, thanks.
There is a maximal quantity until which the thickening is the same as the subset.
Okay. Okay.
Rafael, can I ask a question as well?
Yeah, thank you. Yeah, please.
It depends. It also heavily depends on where you think your points belong to. Because, for instance, if we think these points belong to R2, we could using the same reason construct balls, and then we get the torus, correct? The field torus.
Yeah, but the field torus is a circle.
True.
Yeah.
So we are still we are still in the homotopy of the circle, right?
Yeah. What happens is that if your points are on a linear subspace of your Euclidean space, for instance, if these points they are on a plane, but if I embed this plane in R3 or R4 or any Rn, the homology of the thickenings will be the same than the homology of the thickenings in the plane. It does not depend on the number of dimensions you had. The only thing that matters is what is a linear subspace that contains the points. So don't worry about that.
Okay, thank you.
Yeah, thank you very much for your questions. And this is actually very close to what we are going to study today. First question, how can I choose the values of t here such that my t thickenings are homotopy equivalent to my underlying object? This is question 1. And question 2, once I know these values of t, how can I actually compute the homology of these thickenings? And we are also gonna give an answer to that today. But first, we will have to do some geometry, some Euclidean geometry. And I will introduce the notion of Hausdorff distance and reach. First, Hausdorff distance. Take any subsets of Rn. I will need a very important function, a map that is associated to x. This map is the function distance to x. The distance to x is a map from the initial Euclidean space to R and actually to R plus, you map. Oh, there is a mistake. I hope you can see. You map any point of the Euclidean space to this quantity. Okay, this quantity is the distance from y to x. This is the infimum of the distances between y and the points of x. If my set is closed, I can prove that such a quantity, this infimum, is attained, but it may not be unique. And if it is unique, I can define okay. Something is missing. So if my set is closed, there always exists a projection, the point x that attains this minimum. And if it is unique, I will denote this projection x like that, proj of y on x. Okay. But sometimes there exist many projections, and we will see that. Well, I could give you an example right now. If I consider the circle, this is x, okay? I take a point y in the Euclidean space. The closest point to y is this one here. This distance here is minimized, okay? And so x is a projection of y, and it is unique. But consider the circle too, and think about the origin. The origin admits many projections, because for every point of the circle, this distance here is equal to 1. So actually, every point of the circle is a projection of the center of the circle. Okay. Now, I will define the Hausdorff distance. Take another subset of Rn. I define dh of x, y as the maximum between two quantities. The supremum of the distance from a point of y to x, and the supremum of the distance from a point of x to y. Okay. This can also be written as the maximum of the supremum of the infimum of x minus y, when first I take y and then x, and vice versa. Okay. It turns out that this distance is really a distance, as you may have defined earlier, between compact subsets of Rn. Because if the subsets are not bounded, this distance may be infinite. And you can show something. This is an exercise. You can show that the Hausdorff distance between x and y is also the infimum of the t's, such that x is included in the t thickening of y, and y is included in the t thickening of x. So if x
is there any reason for us to know that in the definition of the Hausdorff distance, for this is a maximum and not a supremum more generally?
You mean this maximum here?
Yes, yes.
This is because we have only two quantities. we have only two.
Okay. I'm sorry.
numbers.
I messed up.
Yeah.
Yes,
Yeah.
of course. Thanks. I'm sorry.
No, it's fine. You could you could say it's a supremum. Yeah. Well, yeah. Only two quantities. And actually, you could define this as the non-symmetric Hausdorff distance from y to x, and this as the non-symmetric Hausdorff distance from x to y. And so I take the max to make this distance symmetric.
Because what I had in mind was one floating point in x and one floating point in y, and then we like computing this distance. But you know, maybe it's the same thing. But
yeah, what you have to do is for any floating point in x, what is the closest point in y?
Yes.
You cannot say the closest, the smallest distance between x and y or the largest. You have to write something like that. Oh, yeah, Lucas asks in the chat, does someone know a good translation for thickenings? This could be nice if someone knows how to say that in Portuguese. In French, it's épaissir.
On dit comment en français?
Épaissir.
Épaissir.
Un épaississement. I think,
épaississement.
Yeah, I think engorgement too sounds fine. Okay. And so I told you that we can also see the Hausdorff distance as the infimum of t's, such that one set is included in the thickening of the other and vice versa. And you can see it in this picture. If x is this point cloud and y this circle, you see that y is included in the 0,3 thickening of x, and also x is included in the 0,3 thickening of y. So the Hausdorff distance is lower than 0,3. Okay. Okay, this is it for Hausdorff distance. Now, I want to introduce the medial axis and the reach. We still have a subset of Rn. I will define its medial axis as the set of points of Rn such that the points such that they admit at least two projections on X. The set of points that does not admit a unique projection. So mathematically, it reads the set of Y's such that there exists 2 points of X, X and X prime, that are different, and such that the distance between X and Y and X prime and Y is the distance from Y to the set X. Example, what is the medial axis of a circle? So as we've seen, every point of the plane admits a unique projection, but the center admits infinity. Okay, let me give another example. I take an ellipse in the plane. You can show that the medial axis of an ellipse is a segment. And you can see that because if you take a point in this segment here, you have always two projections, one here and one here.
Rafael, is it an open segment or a closed one? It seems that it is open because of the extremities, right?
Yeah, it's open because if you take the extremity of the segment, it will admit only one projection. Yeah. But even if you are very close to the boundary, you still have two projections. Okay. What I have more? A point. The medial axis of a point is the empty set. Okay, this is because whatever the point you take in the Euclidean space, it admits only one projection on the point. This is obvious. Okay, the point admits an empty medial axis. And the last example, 2 points in the plane. What is their medial axis? It is their bisector, right? As you may have learned when you were young, the set of points that are at the same distance from 2 given points in the plane is a line. Okay. Now I can define the reach. The reach of X is defined as the distance from the medial axis of X to itself. More precisely, it is equal to the infimum of the distances between a point of the medial axis of X and the set X. Lucas asks, which distance is being used right now? I'm using the Euclidean distance, the 2 norm. You could develop the theory for different norms, even different distances, but the results I will give you today relies on the Euclidean norm. Okay, so some examples of reaches. The reach of a circle is its radius, right? Because the distance of each point of the medial axis, that is the center, to the circle is the radius. This is the distance in red here. The distance, the reach of the ellipse is this little quantity here, the distance from the boundary of the segment to the ellipse. The reach of a point, well, it's an infimum over an empty set, and by definition, this is plus infinity.
Rafael,
yeah.
Is it just me, or the word reach is kind of, it's not very appropriate here, because it seems to me that the reach should be the maximum. I'm just discussing the word, not the concept. Because reach, I mean, my reach seems that it's something that the highest I can achieve, right?
Yeah. And we will show very soon that it is actually a maximum. It will be the maximum of the thickenings we can take. Because remember that
okay, that's
our goal is
why
to
it's
thicken.
reach.
Yeah.
It's two-folded.
Yeah, which will make sense in a few slides. And the reach of 2 points is the distance from the points to the bisector. So this is the half distance of the point. This is the distance between the points divided by 2. And now I can answer your question right now. Why is it called reach? It is because for every value lower than the reach, my space xt, the T thickening, is homotopy equivalent to X. The reach is the maximal value of thickening that I am allowed to go and still have the same topology. I did some drawings.
And they are homotopy equivalent because one is a deformation retractor of the other. Is that right?
Exactly. Because when we are under the ridge, the projection is well defined. You have only one projection, so you can follow the projection.
Yeah, you can follow uniquely back. Okay, that makes every sense.
Yeah, thanks. So for instance, here I took a value of t lower than the ridge, and the thickening of the circle is an annulus. This is a circle. This is homotopy equivalent to a circle. Same for the ellipse here. I took a value of t really close to the ridge. This is still an ellipse, a circle. The point, this is very simple because any thickening of the point is a ball, and this is a point homotopically. And last example, these two balls, these 2 points, if I thicken them not too much, this is still 2 balls, 2 points. Okay, but what happens if I go beyond the ridge? I may obtain something which has a different homotopy type. For instance, here, I went too far, and my annulus became a big ball. And this big ball, this is not a circle, right? The point is not homotopy equivalent to a circle. Same for the ellipse. Okay, this is a big ball, which is not a circle. And these 2 points, they gathered, they connected. And so I have something which has only one connected component, and this is different from the 2 points at the beginning. Okay. An observation here, sometimes you may go beyond the ridge and still obtain something which has the same homotopy type as the initial set. For instance, the ellipse here, even if I go a bit after the ridge, I will still obtain an ellipse. Okay, the ridge only says that while I'm under it, I have something which is homotopy equivalent. And really the proof is very, very simple. In order to show that the T thickening and X are homotopy equivalent, I have to find a deformation reduction. And how do I deform xt on X? I take a point X of my thickening, and I will follow the fiber, the segment given by the projection. Okay. If I take a point here, up, I will project it on the circle, and this will give me a deformation retraction. Okay, so we can now give an answer to our first question. The question being, how can I select a T such that xt is homotopy equivalent to M? So I'm giving you a theorem here, which is not easy to prove, so we won't go through the proof. But basically, we need 2 quantities to make sure that xt is homotopy equivalent to M. We have to make sure that M has a large enough ridge, and that the Hausdorff distance between X and M is sufficiently small. Okay, so the theorem states that my T thickening is homotopy equivalent to M as long as I pick a value of T in this interval. Okay, T must be lower than, greater than 4 times the Hausdorff distance, and lower than the ridge of M minus 3 times the Hausdorff distance. Yeah. In other words, if M is regular enough, if it has a large ridge, and if X is sufficiently close to M, then I can choose some values of T, and we're good.
Rafael, it seems very restrictive this this hypothesis on the Hausdorff distance, because 1/17 is about 0.06, right? So it's about 6% of the reach. It seems very restrictive. Is it?
Yeah, you may say that, but in this example, observe that the reach is 1. Yeah, clearly this bound is not optimal. You can have better. And actually, I have something better for you.
Can I make a quick question just before you
Yeah,
continue?
of course.
Is there you know that in statistics it's very common for us to standardize the data or make transformations. I suppose the transformation won't change the topology, right? I mean, multiply by minus something by a number less than 1. So you can always make or choose a space where the things are less or equal than the Hausdorff distance is less or equal than 1/17 the reach, right?
No, because the reach will also change.
Will also change. Maybe the proof of this theorem is complicated, but is the idea more or less the same of the argument before? These are the bounds that you need for the deformation retract along the fiber to work uniquely. Is that something that somehow the idea of the proof?
Yeah, the idea is that you cannot follow the projection because the projection may not be well defined. You see these balls. If you were to try to retract your set X T to M, you could take the projection of any point of the thickening to M. But when you follow this fiber, are you sure that you will still lie in the thickening?
Yeah, maybe not.
Yeah, maybe not. And you have to use.
You have to be more careful on the proof.
Yeah, that's it. But once you can show that you stay in the thickening, this is exactly the same idea.
Okay.
The result is actually surprising.
Is it?
Yeah, it seems to me. I mean, the condition says that it has to be very close. The Hausdorff distance must be very close. It's just a small fraction of the reach.
Yeah.
So it's surprising that it works at all. Although the idea of the result seems.
Yeah.
But
I don't know. I don't know if that helps, but in my mind, X is like approximating M on some level. So maybe it's not that that artificial to expect that X and M will be close. I don't know. I'm just trying to.
Yeah. I mean the range of T. That there is a range for T.
Okay.
Yeah. Maybe it's strange at first sight, but it feels so natural for me. But I worked with this for the last 3 years. But M must be regular and X must be close to M, so that when you grow balls, they will actually connect one to another and rebuild your set M. Maybe we'll like a bit more this one. This is another version of the theorem, which is exactly the same statements, but with a different interval. And here, there is 2 other conditions. M must be a submanifold. So for those who don't know what is a submanifold, in topology, we work with topological spaces. In differential geometry, you work with manifold and submanifold. So this is a very important notion in geometry. A circle is a submanifold.
Also of interest is the name of the theorem. Some not very well-known guy, Stefan Smale, huh?
Actually, they are very well known in topological data analysis.
I I was being sarcastic.
He was being sarcastic. Yeah,
All right.
Yeah, the
So,
guy is
the guy's
medal.
the guy's a god.
He's a god. Yeah, he's basically god.
Yeah. So that's the hint of how difficult the proof of this theorem might be, you know.
And how hot the subject is.
no,
Yeah.
yeah. You can have a look at the paper. It's readable. I mean, if you have some time to spend.
I imagine so. I'm being sarcastic again.
And I'm pretty proud of this slide because this guy is my PhD advisor, and this guy was in my jury of thesis. Well, so M has to be a submanifold here, and X has to be a subset of M. Okay, so this X here will not satisfy the condition because we are not exactly on M. But we have a nice interval which gives you values of T such that the T thickening is equivalent to the circle. Okay, I prefer this one, the first one, because you do not suppose that X is a subset of M. A question of Tiago: is there any result that gives us an estimate of how many points X must have to see this theorem apply? If we are in a high-dimensional scenario, we will need exponential many. Is it right? So yeah, basically, what matters here is not the dimension of the ambient space, but it is the dimension of your submanifold, of your subsets. Okay, and so to give you an idea, what you need as a number of points is 1 over the reach times the dimension of the circle. If you have a torus, it's of dimension 2, you will need 1 over the reach of the torus times 2. So, yeah, something like that. So again, what matters is the dimension of your object and not the ambient space. Okay. There is some precise results that state that if I have this many points uniformly sampled with some noise, maybe I have with high probability the homotopy type that I need. Okay. And another observation, this is very important to understand that what matters is the dimension of my object and not the ambient space. And this is why people like to do topological data analysis in high dimensional spaces, because even if we are in high dimensional spaces, we may observe small dimensional objects, and the theory still works. Can I have you any reference about that? Well, the best reference about that is the thesis of Eddy and Marie. This is where everyone look for this kind of lemmas. But I will look at, I will give you some papers more readable after the lesson.
Can I just take ask a silly question? In this second theorem, suppose you have like 1 or 2 points. The idea is that the interval is going to be empty,
exactly.
Right? Yeah, okay.
Exactly.
So you have to, because I think that this remark is related to the discussion. You know, you need that this interval to be non-trivial. So you need a certain quantity of points.
Exactly. Yeah,
something like that.
Yeah. In persistent, in topological data analysis, if you don't have enough points, you cannot hope to understand the topology of your point cloud. With the thickening method, there exist other methods.
Other methods,
yeah. But this is another story, right? Okay. Awesome. So this was for question 1. I will get back to that later. Now I'd like to talk about 2 very important structures in topological data analysis: the Čech complex and the Rips complex. Okay. And they answer to our question 2 once I have my T, how do I compute the homology groups of my T thickening? And you've seen, in order to compute homology of topological spaces, we look for triangulations of them, and we compute the homology of the triangulation. It is a simplicial complex. I can use the incremental algorithm, which works very well. And by definition, a triangulation of a topological space is a simplicial complex that is homomorphic to X, right? An observation, we could look for something weaker. We could look only for a simplicial complex, K, that has the homotopy type of X, that is homotopy equivalent to X, right? Because if my simplicial complex has a homotopy type of X, it will still have the same homology groups as X. And I don't know why in mathematics, this object here does not have a name. And this is very annoying when I work. So when I work, I use this word, weak triangulation, to talk about a simplicial complex that is homotopy equivalent to a topological space X. Okay. So be careful with this definition, because I'm the only one on Earth to use that. But I think it's nice for the brain to put a word on this. An example, this is a circle, right? This is a triangulation of the circle, because this is a simplicial complex that is homomorphic to the circle. And this here is a weak triangulation of the circle, okay? Because it is homotopy equivalent to the circle. You can retract the two simplex. And of course, it is not homomorphic. It has a piece of dimension 2 here. Okay. So we will look for something like that, okay? So now, let me introduce another notion, the nerve. And for that, we need a cover. What is a cover? Say I have a topological space X. Think of X as being your thickening. A cover of X is a union, is a collection of sets such that they cover X. Okay? The union of all the subsets cover X. So for instance, here, this circle, I consider 4 subsets of the circles, this arc here, this other arc, we have 4 arcs, okay? This is U1, U2, U3, U4. I draw ellipses around them, but the actual sets are the arcs, right? And then, from a cover, I will define a simplicial complex, N of U, which is defined as follows. You take as a vertex set the set of integers from 1 to n, where n is the number of sets of the cover. And then you will add a m simplex if your sets intersect, if their intersection is not 0. So we will construct the nerve of this cover here. First, I add 4 vertices, 1 for the first subset, 1 for the other one, and so on. Okay, I have 4 vertices, and then I will add simplices. See that U1 and U2 intersect. So we will add this edge here. I have a 1 simplex. Also, U2 and U3 intersect. I'm adding this edge. Same for U3 and U4. And at last, U4 and U1. And you can verify, and you can see that you do not have intersections of more than 2 sets. U1, U2, and U3 do not intersect globally. So these are the only simplices you have in this simplicial complex. This is a nerve. Guilherme, are nerves always uniquely defined? Yeah, once you have a cover, there is only one nerve. Yeah, but there are many, many ways of covering spaces, and they will give you different nerves. What we will see is that if the cover is nice enough, you will have a simplicial complex that is a triangulation or a weak triangulation of your space. Another example, if I take my thickening, my 0,2 thickening, so this is a union of balls, okay? And so my thickening is actually covered by many balls, okay? And I can consider its nerve. So I have a point for each ball that is actually have the same initial points as the point cloud X. And then I will add simplices whenever the balls intersect. So for instance, this edge here corresponds to this intersection between two balls. Okay. But here we have higher dimensional pieces, right? For instance, here we have 3 balls that intersect. So I have to add a 2 simplex here. Here I have even 4 balls that intersect. So I have to add a 3 simplex. Okay. I have in this nerve simplices of dimension 2 and 3. Notice that this simplicial complex is not a circle, but anyway, this subset here, this thickening is not even a circle. Okay. Actually, this simplicial complex has the homotopy type of this one. They are both points. What if I take the 0,3 thickening, same construction, I take a point for each ball, and then I connect the balls and I add simplices. And in this case, we have very high dimensional simplices. For instance, here I have a 6 simplex because I have 7 balls that intersect. But whatever, because this simplicial complex here, it has the homotopy type of the circle. Okay, this is a weak triangulation of the circle, and this is what we are looking for. And fortunately, we have a theorem which states exactly that. This is called the nerve theorem, a very important theorem in algebraic topology. So I was saying that we have this very important theorem of algebraic topology, which states the following. If my cover is a cover by balls, for instance, in this thickening here, I have covers where every element of the cover is a ball, then my nerve is homotopy equivalent to my space X. This simplicial complex is homotopy equivalent to the thickening, and this one here is homotopy equivalent to this thickening. And I should say that, so this is a version of the nerve theorem for balls, but you have more general versions of this theorem. If you are in the Euclidean space, you can only ask for the elements of the cover to be closed and convex sets. But it also works in any abstract topological space, and you will ask for the intersection of the sets to be contractible. Well, here we only look at balls. So this is the one we need. And so, yeah, I will give a name to this simplicial complex. So we have a finite subset X, which is simply the points, right? And I consider Vt to be the collection of balls of a radius t and centered around every point of X. So the union of each balls, the union of the elements of Vt is the T thickening, right? Well, I consider its nerve, and I call this the Čech complex of X. And as I have a parameter T, I will call that the Čech complex at time T. Yeah, the T thickening is a collection of closed balls. I denote the closed balls with a little bar over the ball. Okay, and you can see it from the definition of thickening. This is lower or equal to T. Okay. And okay, awesome. Now my Čech complex, it has the homotopy type of the thickening, and this is a simplicial complex. So we solved question 2. We know how to compute the homology groups of the T thickening. Okay. Of course, this is not the end of the story. I want to present to you another complex, which is called the Rips complex. And it is the one that people prefer in practice because it is easier to compute. Thiago?
Yeah, that is because the Čech complex may be very, let's say, wasteful, because if you have many intersections, then the dimensions go, the dimensions go up without adding to the homologies, something like that. I don't know.
Yeah, actually, we will define a complex which has even more simplices than the Čech complex. But as you will see, this will be easier to compute anyway. And Thiago asked, what is the intuition behind close points defining high-dimensional simplices in Čech complex? Really, having high-dimensional simplices should be seen as an artifact of the consequence of the construction, which does not have really topological meaning. It's just because you have so many balls, you have so many intersections that you have high-dimensional simplices. But topologically, there is no reason, no intuition. It's just a combinatorial thing. Okay. So how do we actually compute the Čech complex? We have to look for intersections, right? Xt, the T thickening. In order to find the simplices that compose the Čech complex, I have to check whether intersection of balls is non-empty. And I should do that for any combination of balls in my cover. So first, I have many different subsets of my cover. And moreover, when I am given some balls, this is not trivial to test whether they intersect. If I give you, say, m centers and a value of a radius, can you tell me if the balls with these centers and this radius intersect? This is called the smallest circle problem, or the smallest sphere problem. So this can be solved in linear time, but linear in the number of points. And so you may have very huge number of points, right? And moreover, you have to check this for many different subsets. So in practice, this is very costly. And I want to describe a simpler version of it. Yeah, it's linear, but you have to do it many times. You have 2 to the m different intersection to consider. All right, the power set of the cover. So it's 2 to the m times linear. We will first define clique complexes. So this is a notion in a graph theory, in simplicial complexity theory. Say I have a graph, G. Question. Can we use a sample to avoid points that are close for large amounts of points? Yeah, this is something people did a few years ago. Subsample your point cloud, you will have less points and less intersection. So this is something which works very well in practice. Yeah, you can do that. But actually, people also like to subsample and use these things that I will introduce to you right now. Okay, a graph, what is it? It's vertices and edges. Okay. I will define a clique of a graph. A clique is a set of vertices such that for every pair of vertices in these subsets, the edge belongs to the graph. So there is a mistake here. For every VI, the edge VI. Okay. For every pairs of 2 elements of my clique, the edge belongs to the graph. So for instance, this thing here is a 2 clique. A 2 clique simply is 2 points connected by an edge. Okay. This is a 3 clique because I have 3 points and they are all connected by an edge. And on the left, this is a 4 clique. Okay. So a clique is a subset of vertices such that the induced graph is complete. Okay. This is a complete graph on 4 points. All right. Now I will define a simplicial complex on top of a graph. I will call it the clique complex. And the clique complex of a graph is the simplicial complex whose vertices are the vertices of the graph and whose simplices are the cliques of the graph. Okay. For instance, here I have a 3 clique. I will add the corresponding triangle, which is a 2 simplex. I have a 4 clique that I will consider the 3 simplex. Okay. I add in my simplicial complex the subset of vertices that consists in the vertices of the clique. And you can verify that a clique complex actually is a simplicial complex, right? If you take a simplex and one of its face, the face is in the simplicial complex. Remark that if I have a clique complex, its one skeleton is the graph. Okay, the one skeleton is the simplicial subcomplex that consists in the simplices with dimension at most 1. So the vertices and the edges. So I can recover the graph from the clique complex, and I can define the clique complex from the graph. Okay, so we have a bijection. I was saying the graph entirely describes the clique complex, and also from the clique complex you can obtain the graph. So this is why in practice this is interesting to use, because you actually have to store in memory simply the graph, simply the one skeleton. And you can deduce the whole simplicial complex from only the data of the one skeleton. And what about the faces of these simplices, Lucas? Yeah? Do you want me to explain this exercise?
Sorry, Professor. I was talking about you defined the simplices of this simplicial complex, the cliques. But what about the faces of these cliques? Are they have to be in the simplicial complex, right?
Yeah. So for instance, this 3 simplex, I added it in the simplicial complex because I have a 4 clique, right? But you can consider this subset of the 4 clique. This is a 3 clique. And so we add also this triangle to the simplicial complex. Okay, cool. Yeah, a subset of a clique is a clique. Okay, and now I can define the Rips complex. So I still have a subset, a finite subset of the Euclidean space, and a value of thickening, a value of t. I will consider a graph, G to the t. This is a graph whose vertex set is the integers from 1 to n, or you could say the points of x, and whose edges are the pair of points such that their distance is smaller than 2 times t, 2 times the parameter. Okay. So for instance, if I had these points in the plane, I take a value of t. Okay, so this will be 2t, and I add an edge between each pair of points that are at distance lower than 2t. This will give me this graph. Okay, and you can remark that this graph is actually the one skeleton of the Čech complex. Remember, the Čech complex is the nerve of the union of balls. But 2 balls intersect if the distance between their centers is lower than 2 times the radius. So this is the exact same construction. Okay, for instance, I have 2 balls intersecting here, 2 here, and 2 here. This gives me this triangle. Okay. And now the Rips complex at time t will be the clique complex of this graph of JT. Okay. And I denote it Rips t of x. Of course, it depends on the parameter t. And to continue this example, the clique complex of GT here will be this graph. This will be the Rips complex at time t. I have 2 3 cliques. So 2 simplices. Remark that this may not be the same simplicial complex as the Čech complex, right? This is the Čech complex at time t of x. I do not have a triangle here. I do not have a 2 simplex, right? Because these 3 balls, they do not intersect globally. They intersect 2 by 2, but not altogether. So I do not have in my nerve a 2 simplex here, though I have it in the Rips complex. Okay. This is what I drawn here. The Rips complex may not be equal or homotopy equivalent to the Čech complex. However, they are connected by a relation that we call interleaving. And it reads as follows: the Čech at time t is a subset of the Rips at time t which is itself a subset of the Čech at times 2t. If you double the radius of the balls, your rips is included in the Čech. Okay. Oh, I forgot an edge in my Čech complex here. So this example is a bit trivial because the Čech complex at time 2t, as you can see, is a very high dimensional simplicial complex that is actually homotopy equivalent to a point. But this may not be the case always. And I'd like to prove that with you. So first, let us show that the Čech is included in the rips. And this is actually very straightforward to see because the rips is the Clique complex of the one skeleton of the Čech. And the Clique complex is the maximal simplicial complex you can build given a skeleton, given a graph. Okay, if I give you a graph and you compute the Clique complex, I cannot add any simplex without modifying the underlying graph. I have to add edges. So really, this is a matter of definition here. The Čech complex is a subset of the rips complex. Now, let us prove that the rips is a subset of the Čech if you double the parameter. Well, choose a simplex in the rips, and let us prove that sigma here, not omega, sorry. Let us prove that sigma is in the Čech. We have to prove that the intersection of the balls of radius 2t for the centers being the points in the simplex, we have to show that they intersect. Their intersection is not the empty set. But if I take any vertex, let us pick any vertex of the simplex. Okay. For any other vertex, I have that the distance between x and y is bounded by 2t by definition of the rips complex. So it means that each of these balls contains x, the vertex I choose. So x is an element of this intersection of balls. Okay. And we deduce that this simplex is in the Čech of parameter 2t. Okay. You could, so what we have done here, I can write a sentence. If you have pairwise intersecting balls, doubling their radius is enough to make them intersect globally. All right, and so we have that the rips is interleaved with the Čech. And so what may be a bit paradoxal is that the rips is more complicated than the Čech in the sense that it has more simplices, but it is less complicated in the sense that it is simply described by its underlying graph. Okay. So this is all that I wanted to present you today. The problem of topological inference and here homology inference ask two questions. So from a thickening perspective, how can I find nice thickenings and how can I compute their homology? And we've seen a solution of the existence of nice thickenings thanks to some Euclidean geometry, the reach, the Hausdorff distance. And we computed their homology thanks to some complexes such as the Čech complex and the rips complex. I would like to say something here. We have I presented these two theorems, right? That states that we can find a value of t such that my thickening has a homotopy type of my underlying set. But can I really choose a value of t thanks to this theorem? I can't, because these values, I don't know. I don't know what is the Hausdorff distance between x and m, and I don't know what is the reach of m, right? Because I do not have access to m. So yeah, this is not a very satisfactory answer. And yeah, actually the good answer to this question, how can I select thickenings? We will see that next week in persistent homology. Persistent homology really is about how can I select these thickenings. All right. And yeah, so please have a look at exercise 37 for tomorrow. And thank you, everyone.